Good afternoon, everyone. I'm gonna stay sitting like this because I'll be talking for an hour. So I hope you will forgive me, and also that everyone on the call can see me and hear me. Um, Thank you for coming also for this afternoon session. My name is Eliška, and I'll be doing this hands-on workshop on transpiling quantum circuits with Qiskit. So what are we going to do today? Because it should be a hands-on workshop, it should be a little bit more interactive than just the general talk. We'll see how that goes. And I have some small activity for you right at the beginning. Before I introduce myself, I want to know to who I am actually talking to, because I don't know neither background of you sitting here in the room and also of the people on the call. So for you sitting in the room here, no, I don't worry. I'm not gonna ask you questions and stuff like that you have to talk, but you can answer just by raising your hand. So my first question is who from you sitting here is still a student? And okay. Bachelor level one. Okay. Someone doing masters? One. Anything above? Okay. 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 Now what's the rest? Okay. I'm not gonna need you to talk. So, another question. What's when it comes to your experience with quantum computing, specifically working with IBM quantum hardware, do you have any experience with it? Okay. Do you know what transpilation is? Nice. Kinda. Okay. And when it comes to the experience with transpilation, is it like a big experience or just like a little bit? A little bit. Okay. So you heard about it, you may try it sometimes, but like nothing big. Okay, cool. Now the same questions go to the people in the chat. I will ask, I guess, Abu to sometimes give me the answer so I don't have to switch all the time in between. So for the people who are watching us online, if you can quickly summarize what's your background in terms of these questions. So whether you are a student or not, on which level, and whether you have a experience with working with IBM quantum hardware and with transpilation. So
we have one student did quantum teleportation master thesis and he wrote coach. Let's wait, some others can answer.
Okay.
Ask several things.
Yeah. Yeah. Okay, so now I can introduce myself. So who am I? So hi, I'm Eliška. I'm a PhD student. I'm in my first year of PhD, and I come from Czech Technical University. And I do research on this long buzzword, which is called quantum computing methods for malware detection. I'm not gonna go too much deep into it, but it's kind of relevant for my background for this workshop I have here. I'm not a physicist. I have background in computer science and specifically with computer security. And yeah, for a while I I have some experience with quantum computing, let's say. I got to it when I was doing my master thesis on the same topic, and I found out there are many questions to answer, and I have so little answers, so I decided to follow up on that with my PhD. So that's what I'm doing right now. And yeah, so my vision of what I'm trying to do is to do some practical application of quantum computers we have available like in this time. What does it mean? So if I should summarize what I do, so malware detection, that's some binary classification problem of answering a question whether some software is malware or not. Then you have machine learning. So it is to answer this question, if something is malware or not, we can use machine learning to train some model which will do it for us. And when you mix it with quantum computing, that's where the fun begins. So I do kind of hybrid quantum machine learning stuff, which means that I partially use classical machine learning and partially quantum machine learning. So it all connects together. And
there are both. Some experts even
okay,
intensively, some even they don't touch.
okay. Yeah, where was I? Yeah, and how is it connected with this talk today? I focus on working with real quantum hardware. So my research is more practical than theoretical in terms of I try to write software for the hardware and run it on a hardware and see how it's gonna end up, like whether the results I'll get from running the program on real hardware, whether they are somehow useful, whether we can use them for some practical application, not just like running some circuit on the hardware and that's it. And I work with IBM quantum hardware. The reason for it is that like IBM quantum hardware is like I would say the most like open source quantum hardware we have available. And yeah, that's what I'm gonna be talking about today. Yeah, and how is it connected with transpilation? So in the adequate course some of you might have took, you probably wrote some software, some like pieces of software. By software, I call whatever is like some code snippet you write in Python and try to construct some quantum circuit. And when you write some quantum circuit with for example, with Qiskit, you have like something like I would say theoretical code in terms of that when you want to actually run it on the hardware, you cannot run it just by like saying this qubit will be connected with this qubit. We will apply these gates I've chosen, and we will measure it this and this, and that's it. You have to somehow compile it, so it is the code is specifically dedicated for the hardware you are working with. To have some example from classical computing. For example, when I would want to write a application for my phone, I would write it in some high-level programming language, for example, in Python or Swift. And to actually run it on the phone, I would have to compile the code into the into the assembly instruction, which are specific for the hardware I'm working with for my phone. And the same thing you have to do with the circuit you write using, for example, Qiskit. Qiskit, because we are working with IBM quantum hardware. You have to somehow translate the circuit into a set of gates and stuff like that to run it on the hardware. So, to get back to this, so quantum computers have physical constraints such as limited qubit connectivity and a restricted set of native gates. What does it mean? That on real hardware, not all qubits are directly connected together. That's one limitation. And the second thing is you have not all the gates available. So for example, some example of some quantum gate. For example, I don't know, Toffoli gate won't be available probably on most of the hardware because you have simple gates available there. So if you would have a circuit which is working with Toffoli gate, you would have to translate it into a circuit which does the similar job, but doesn't use this gate, but like different gates which are somehow replacing the stuff the Toffoli gates should do. And this process of the translation from one circuit to an equal another circuit is called transpilation. And so the first thing we do through this process is that we match the topology of the hardware. So we map the logical qubits we have in our theoretical quantum circuit. We map it to the real qubits on the hardware. So we have the qubits we need to have connected. And we use a different gate set, which we can execute on the hardware. This process consists of some few steps. One of the main focus, or at least for me, when I do the translation, is reducing the circuit depth, which is the number of the layers of the gates, minimizing in general the number of gates, so you don't have too many of them. And the most important part, mapping the logical qubits to the physical qubits. So the qubits which has to communicate together can communicate together. I prepared some Jupyter notebook with some practical example of what I'm gonna be talking with. No, I don't want you to like code with me. You can. Abu, have you sent the? Yeah.
Check the
Yes.
access.
If you want to, you can access the notebook in the chat to this meeting, and you can run it with me, or you can just like watch me and ask questions, or I will ask questions from you. Okay. Okay, what's the time? Okay, nice. So, how to start? How you can even access the IBM quantum hardware? That's the first question. When I talk about what I do for my research, people surprisingly a lot of people ask like whether I ever seen the quantum computer in real life. Have you ever seen the quantum computer in real life? Okay, cool. Wow. So I can show you how the real life quantum computer looks for me. So this is how I see the quantum computer. This is a web application. It's called IBM Quantum Platform, and it's just like some web UI which shows me all the quantum hardware I have available for my license. And yeah, so that's how quantum computer looks for me. You can actually access this as well, and that's what I'm going to show you through this workshop. So you as well can run your some quantum circuits, some code on the real hardware as well, and not as part of this workshop only, but you can try it whenever for whatever purpose you have. Yeah, so this thing is called IBM Quantum Platform. I linked it into the notebook. I don't know if you sitting in this room do you have access to the Teams chat as well? Do the participants here have the access? Okay, so I'm gonna share with you after this workshop, I guess. Yes, but so you can create account there. I've already am one step ahead, so I created a dummy account there. Anyone who creates a account there, it's for free, and you can access the hardware for I think 10 minutes per month, something like that. It looks like this. Here is a summary of some jobs I've run run on the platform. The important thing you have to find from this after you sign up, I'm not going to go through the sign up process. I hope that you are able to go through it yourself. But the important thing for running the code is this API token. It is like something like a passport to access your instance. I'm gonna pass it here. It's just a dummy account, so you shouldn't be sharing your token with anyone, but I'm gonna do it. And when you're doing it for the first time, you have to import the Qiskit get time service. You have to set up your credentials to work with your account on the platform. I did it here, so I guess I don't have to go into the details. And whenever you want to work with run some code on the hardware, you have to first set up this service object, which basically tells the IBM Quantum Platform that it's you. So we have it. And the same way as you can see the resources online here like this, you can do it the same way in the code. When I run it, you can see I can only access 2 of the backends from all the backends I have here, and that's because not all of them are available for the free license. So we can access 2 of them. Where is it? Yes. So you can either from these backends select some specific backend, or you can select the least busy one, which is usually the best option because especially for the free access, you are not the only person who wants to run their code on the hardware. So usually there is some waiting line for the hardware. So you want to go to the line which is the shortest one. So that's what this command is handy. And we can get some info about the backend. Here it is in the like a print form, but I'll show you, I guess, more visually. So here we can see how many qubits the backend has and what's its name. And I've listed also the instructions there and what's this qubit layout. I'll show you here. That's this thing, and this tells us like which qubits are connected directly on the hardware. So for example, if I would have a circuit which uses let's say 15 qubits, and I have some gate which directly connects qubit, first qubit and 15 qubit in my ideal circuit, I would have to transpile the circuit in a way that these 2 qubits are mapped to different physical qubits so that they are directly connected. That's one thing. Or I could add some swap operations and like through more operations, like connect them so they can communicate together. So that's like one of the main constraints when it comes to the hardware. Here you can see which gates are supported for this hardware. So you can see that the set is very limited. Then you have here a bunch of other information, for example, like how many jobs are there running right now, but and that's like not so important. Oh, and also another thing, most of the hardware is located in the US. The name is kind of misleading most of the time. Yeah, where's the code? Okay, for first question, either to both people online and to people in the room. Is it somehow understandable so far? Yes, thank you. Thank you. And anyone in the chat? Am I going too fast or too slow? I hope I'm not boring you already. Okay, so back to the presentation. Where do I have it? Right here. Yeah, here's just a recap of a bunch of buzzwords I said already. So the access token is for accessing the hardware. Service is for communicating with the platform. Backend is just a different name for the specific quantum device. Least busy, it's usually the most important thing for you because you want to wait in the shortest line. And coupling map, that's a different name for the layout of the qubit or topology of the hardware. It all refers to the same thing, and that's the layout of how the qubits are connected. Yeah, so the transpilation process, when it comes to like the coding stuff, it has a lot of stages. Each of these stages does different stuff. As the name suggests, some of these stages cares about the layout of the qubits. Some of them cares for when you translate the circuit to the when you finally translate the circuit to the gates which are on the hardware, the circuit might need some optimization because it will be very complicated when it comes to depth and everything. So we want to optimize it to do it the smartest way possible. So that's all these what all these stages of the transpilation process do. And they are called transpiler passes. Now, why is it important? Pass in the Qiskit language is the smallest unit of the transpilation process, and it's like some object which does some specific circuit transformation. Here I added some example of some transpiler pass, which is kind of understandable from the name. So what, for example, this transpiler pass do is that you have some gate which acts on more than 3 qubits, and you want to decompose it to only two gate qubits operations because of the layout and because you have usually only 2 qubits connected together. So what this pass do is that it decomposes the operation that acts on more qubits to something simpler. Why is this important? I'm going to go back to the code. You don't have to like do all these passes yourself. You can use a thing in Qiskit, which is this function, which is called generate preset pass manager. And the pass here stands for the transpiler pass preset because it is preset already and it will generate it for you. And I'll generate it here. You can choose first the backend, so the real device on which you target your transpilation, and you can choose from different optimization levels. 0 level is like the zero, no optimization, like the most straightforward translation possible. It's usually the fastest one, but the circuit which you get after this is usually pretty complicated or useless. I will show you on the example. For the example here, I'm going to be using this type of circuit. It's called ZZ feature map. Hands up if you know what this circuit stands for. Okay, I'm going to explain it. And in the chat, someone, can you check the chat?
I'm checking.
Yeah.
The question about transpilation.
Oh, okay, thanks. So this circuit, it's a predefined circuit in Qiskit already, and it's a type of parameterized circuit, which means that you can set some parameters for the circuit, which controls the certain types of the operations on the circuit. And I'm going to use it here just for the example for transpilation. So here I import the circuit, distance that I want to use for qubits. I want to have one layer and I want to add some measuring, and I will draw it how it looks like. So here you can see the circuits, here are the gates, here are some measuring operations. I can see that I have 12 2-qubit gates, this is the total depth. And now my goal is to be able to run this circuit on the real hardware. So I have to transpile it because I have operations which are not supported by the hardware. So I'm gonna use this preset path manager, which will do the transpilation for me. I have 0 optimization level, so it's gonna be fast, but probably the transpilation is gonna be pretty bad. I have this helper function here, and we're gonna transpile it and draw it. And here you can see how much the circuit has changed after I transpile it. The reason why I chose this circuit is because I didn't want to, so first look at this sample circuit at the beginning, at the depth and number of qubit gates, and how it changes after transpilation. So the depth goes from 18 to 170. 2-qubit gates grows a lot as well. And from this simple circuit, it grows to something like this. This circuit should do the same job as the circuit before, but now it actually can be executed on the hardware. And why am I showing you this? It's because like this circuit is something, is a type of circuit I use in the stuff I am doing for my quantum machine learning research. And it's actually a pretty practical, one of the main issues when it comes to like trying to do some application on real hardware is that you have all this theoretical research for how the circuit should look like. For this circuit, what it does, it does encoding of classical data into quantum circuits to like use it then in the machine learning process. So you have this nice theoretical circuit, which is based on some research and stuff like that. And you're like, okay, it should have it should do this and look like this and have this small depth. And you are like, okay, I'm gonna run it on the real hardware and see how what the results I'm gonna get from it. But I have to transpile it, but whatever, it will be the same circuit which does the same job. You transpile it and you see that the circuit changed a lot. It's suddenly this complicated. The depth, for example, when it comes to execution of how long it will take for like the circuit do its thing on the hardware, the depth will make the computational time grow a little bit. And for example, in machine learning, you have to execute this circuit many times. So when you have a growth of a few seconds for this complicated circuit on one run of this circuit, it will grows up a lot when you want to execute this circuit for a huge number of samples. So for example, this is an issue. Then the question is, will the circuit do the same thing as I wanted? Will be the results from this complicated circuit somehow usable for the problem I'm trying to solve? And why is it important to think about it? We have right now, when it comes to research and stage of the quantum computers and everything, is that we have a pretty solid like theoretical research, for example, for machine learning. Quantum machine learning is promising like a promising way of how to use the quantum computers we currently have, and why it is promising theoretically. The issue is that when you want to run it on the hardware, the question is how we're gonna validate this promise, when the circuit completely changes. And yeah, I hope it makes sense, but that's what I'm kind of trying to answer. Is it just promising or is it usable practically? Again, are you still following? Is it somehow understandable? Good. Thanks. No one in the chat. Okay.
That's a good question.
So you're okay. I'm gonna go back to the presentation. What do I have here? Yeah, so just a recap of what I was talking about. The important thing for you, if you want to run any circuit on the hardware, you can design all the transpilation passes and everything yourself. But when you are starting, the easiest way to just see whether you can run something on the hardware is to just use the already implemented stuff, which do it for you. So for the beginning, I recommend just use the preset stuff instead of doing it yourself. And for the optimization level, I can show you that when I change the optimization level to something higher, right? Let's change it to the highest number of optimization is 3. So it's gonna take a little bit longer. So you can see I used the highest level of optimization and I still ended up with circuit with depth of 76. So even a comparison that at the beginning I used the worst type of optimization, even when I make it to the highest one, I still end up with pretty complicated circuit. So yeah, it's not as easy as it seems. Yeah, to run the circuit on the hardware, it doesn't end up with transpilation, unfortunately. You have to work with a thing which is called in Qiskit a Qiskit primitive. It's something which what it does, in my words, what it does, it helps you to prepare the computational job, which contains your circuit with for example, for me, because I use parameterized value, it will contain the values of the parameters for the circuit and the circuit itself, the transpiled circuit, and you use it to just communicate again with the hardware. It's just like another level of abstraction. There are 2 types of Qiskit primitives. One of them is estimator, one of them is sampler. For me, for my case, the more interesting one is the sampler, because at the end, I care about like when I measure the qubits, I care about the bit strings of the qubit, if it makes sense. Yeah, are you following? Yeah. And there's another thing which you might occur when working with the hardware. There is a thing, a data structure, which is called PUP. It stands for Primitive Unified Blocks. I actually found out what this shortcut means yesterday. By the way, it's pretty hard to find it even in the documentation. It's nothing super important, but this PUP data structure is something you put into the computational job to be able to run the job on the hardware. I'm gonna show you in the code. So yeah, here in this last section, I just created some random parameters for the feature map. I assign it, and so here are the random parameters. Here you can somewhere see that it changed numbers. And the last step is to use this primitive, say that I want to work with my chosen backend. I use this pop, which is basically just my transpiled circuit with the parameters assigned. And I use it for running the computational job. So I'm gonna execute it here. Hope it's gonna work. And I'll go back to the IBM Quantum platform. There's this thing called workloads. And let me check the ID. Should be this one. So here I can see all the jobs for my dummy account. The one I just submitted is the last one. And I can see that it is completed. So it means that the circuits run on the hardware actually. It measured something, and here I can see the circuit as well. And to get the results, I have to go back to the code. I've saved the job ID, so now I can see the bit streams. Are we still following? Yeah. Yeah, so the reason why I mentioned this pop thing is that you can actually put like more of these pop things into the computational job. It is more like a software struggle than that it would be somehow relevant to the theory. Because, for example, for me, just to figure it out, that how should I put this data structure into the sampler argument was a fight. So yeah, that's what I showed here. Yeah, so recap. To be able to run the job on the hardware, you have to work with those Qiskit primitives. You choose the primitive based on the type of information unit you care about. You either want to have some observable, or you care about the probability distribution or the probability distribution. The important primitive is the sampler. Pop is just the data structure you put into the job. And the important thing is this computational job, and that's what's then executed on the hardware. Yeah, I made it on purpose, kind of more simpler in terms of that I skipped lots of obstacles you can find when you are trying to do the transpilation yourself. But I hope you have got some general idea about what the transpilation is and what's the main issue. The main issue is that you have this, whatever circuit you have for your problem at the beginning is this nice ideal circuit. You transpile it and you get this. And that's the main issue, and something I'm trying to make a little bit better in the research I'm doing to make this circuit more optimal. Or yeah. Are we still following? Didn't make sense. Yes.
Sorry.
Pop. It's just a data structure. Is the thing you have to put into the sampler. It's yeah, basically your circuit, and you could add more parameters. If I wouldn't assign for example, I'm using parameters by a circuit, so I could either assign the parameters to my circuit or put it here, or I could specify the number of shots and stuff like that. And it's just like a data structure, just a software thingy you have to think about when you want to run the job, that you can just do. If I were to do instead of this, only this, it wouldn't work out. So I mentioned it not because the pop is so important in terms of like what the shortcut means, but more so that it's just that the Qiskit code, when you want to run the job, is not so self-explanatory. Yeah. Do we have any questions in the chat or not? No? Okay. With you in the class, I'm gonna figure out how to share the notebook with you. Those who are joining us online have the notebook already. So I hope that I encourage you to try it, to just create the account on the IBM Quantum platform and try to run some simple transpiled circuit and job there. I think it's nice to have that experience to not just run something theoretically on simulator, but on real hardware. And you can do it for free, at least for now, because the hardware is accessible for free for some limited computational time per month. And yeah, that's it. I have the last slide. This is how I edit prompts to ChatGPT, how it imagines me working on the quantum computer. So that's just like a fun thing. If you want to reach out to me and ask me about something, this was I guess very like not too much in depth. So if you have more questions, I can talk about this forever. So you can reach out to me. And now questions. Yes. 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 Yeah, short answer is yes. Yeah, you can also, as the part of the optimization and stuff, you can set also like different parameters on how the on the error correction, error mitigation. Yeah. So short answer is yes. Long answer is you have to fight with the documentation for the transpilation. So that's why I skipped it in this. Yeah, but the same as with the just the translating the gates and everything. It's unfortunately not as I would say like not as simple. uh, I think that for the preset path manager, you can specify it in the parameters for the preset path manager, and if you want to play with it more, you can create your own transpiler path, specify, or you can either create the transpiler path completely from scratch, or you can choose from some, again, pre-made in the Qiskit. You can like decide which passes you want to use, how you want to like follow them. So you can get quite a lot of results for transpiling just one type of circuit. Yeah.
There's one question.
Okay.
It's very simple, but maybe you can hear your answer. How to learn Qiskit basics and use of it.
Oh, okay. Oh, so am I on the who's the yeah, I have to remember what's the I think it's learning something. Because IBM has in general like nice resource materials for like learning the I'll show you on my dummy account because this is oh, and one more thing, when I do the research and stuff, I have access to like more hardware devices and everything through the license I have thanks to CTU. So that's why I'm showing it all on the dummy account, because I want to show you how it would look like for you if you would try it yourself. But just in general, IBM or Qiskit has a nice like learning materials. When I was starting with like writing quantum computing code using Qiskit, I learned a lot just from those materials. There is this page, it's called learning.quantum.ibm.com. There they have some courses or learning paths. Also, when it comes to documentation, where's the documentation? Yes. So it's on the learning. So you can. The documentation is sometimes good, sometimes bad. Depends. But like lots of things you can also read from the documentation, and yeah. So I would suggest short answer to explore the learning part on the IBM Quantum. Yeah.